we're going to look at section 3.6, absolute value functions. We're going to specifically look at graphing an absolute value function. You've already worked on solving absolute value equations. The first thing you should know is, what does the absolute value function look like when you graph it? So here's what it looks like. How do we get that? Well, if we substitute some values, let's say we substituted -1, let's go -2, -1, 0, 1, and 2. Those are our x values. Y is equal to the absolute value of x, so the absolute value of -2 would be 2. The absolute value of -1 is 1. The absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. So graphing those points, we have -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. Okay. We know that we could continue to use x values that were greater than 0 or x values that were less than 0, and they're going to have the same mirror image on both sides because the absolute value is going to make it positive. We could also substitute values such as -1/2, and we're still going to see that our values are going to line up in a linear fashion. The absolute value function, of course, can have different ways of appearing. Notice, however, no matter whether it's been shifted up and to the left or to the right or reversed or reflected over some axis, that we still have that V shape. So what you need to remember is that absolute value, is always going to have that V shape to it. Absolute, I only have one E in absolute. It's always going to have that V shape to it. We're going to look now at how we get these different kinds of graphs. We're going to introduce ourselves to something called transformations, which you'll hit much harder when you go to class. Okay. We're going to skip this section. You can stop this recording and review it if you would like, but you've already covered this back in section 2.6. Okay. So we're going to graph this and make an observation. So we have our basic function y is equal to the absolute value of x. We call that our parent function, the absolute value of x. And it has that nice V shape, and it's symmetric on either side, going up with a slope of up 1 over 1. You can see that it's like a line that's been cut in half, and right there at the 0, 0. Okay. So next we're going to look at the absolute value of x minus 3. So notice we've substituted some values, -2, -1, 0, 1, and 2. We've substituted those into the function absolute value of x minus 3. The first one, we have the absolute value of -2, which is 2. Minus 3, we get -1. Absolute value of 1, which is 1. Minus 3, we get -2. Absolute value of 0 is 0. Minus 3 is -3, and so on. When we substitute these values, graph these values, we have -2, -1. There it is. We have -1, -2 right here. We have 0, -3 right down here. We have 1, -2, and we have 2, -1. We can see very clearly where that bottom part of the V is. That's what you need to look for. So we're just going to then make that nice V shape going up on either side, because that's the pattern we can see. Okay. So when you observe this, what does it look like happen between the blue line or graph and the purple one? You can see that it's been shifted down 3 units, right? So the parent function, y equals absolute value of x, for this new function, g of x is equal to the absolute value of x minus 3, it's been shifted 3 units downward. Okay. So what do you think our function would look like if we wanted to have a function that takes that blue line and shifts it 5 units upwards? And we can check it, right? So let's just take a value and check it. First of all, what would 5 units upwards would look something like, like this, right? Oops, not so good with this pen. There we go. Pretend like those are straight lines. Okay, so for example, when we substitute 0, we want to end up with 5. So let's see, if we put 0 in here, 0 plus 5, yep, that would be 5. Absolute value of 0, 0 plus 5, that would still be 5. 5 times the absolute value of 0, nope, that would be it. That's definitely not it. Okay, let's try a different value. Let's try a negative number to see what happens. Let's put in -1, and we're hoping that we get 6, right? So if I do the absolute value of, So if we put in the absolute value of, okay, I'm going to do it up here, the absolute value of -1 plus 5, that gives us the absolute value of 4, which is 4. That did not work. Let's try this other one. If we put in the absolute value of -1 plus 5, that gives us 1 plus 5. That's the answer we wanted. So remember that the absolute value of x minus 3, where this minus 3 was on the outside, shifted us 3 units down. This absolute value of x plus 5, where that plus 5 is on the outside, shifted us 5 units up. So what we want to write here is the absolute value of x plus 5 would be our function h of x. That would take our original function y equals the absolute value of x, or f of x is equal to absolute value of x, and shift it up 5 units. So in general, if we have f of x, if we have some function g of x is equal to the absolute value of x plus c, if it's plus c, we're going to go up c units. If it's minus c, we're going to go down c units. Of course, you don't have to know this rule straight away. You can keep just trying out the numbers and see which ones work. This is a kind of experimental phase that we're going through, but soon enough we're going to get to transformations. So we have another one. Notice the location of the constant 2 is inside the absolute value symbol. So there again is your original parent function, f of x equals the absolute value of x in blue. All these values have been substituted, -1, -2, 0, 1, and 2. Notice that gave us all the red dots, but we wouldn't have had that V shape yet. You have to keep going until you find the V shape, and we're going to talk about some ways to do this in the next class. Okay, so we keep going by substituting values until we get that V shape, and now we can see right where that function is going to be. So now what's happened to the blue line? Instead of going up or down, it has shifted left 2 units. Where did that 2 come from? It came from right here. That plus 2 inside the absolute value actually shifted us left 2 units. There are 2 ways to remember this. One is, how would I get myself back to 0 for what my function value? I'd have to put in a -2 for x, right? So I'd have to decrease my x value by 2 to get back to the original values that I had for my output. The other way is to just think of x as being naughty, right? It goes in the opposite direction. When it's inside with the x inside the function, it's going to go in the opposite direction that your brain tells you it should be going, right? So the plus 2 is actually going to go in the negative direction 2 units, right? All right, so what's happened here is the parent function has been shifted 2 units to the left. So now, give this a try. We have a new function. We want to shift 5 units to the right. What would it look like? So first of all, what would it look like in the graphical form? So we know we take this blue shape, we go 1, 2, 3, 4, 5 units to the right, keeping that same shape, we expect to see something like this. Knowing what the description is, it gives us an idea for what numbers we're expecting when we put it into our function, right? So let's try these. Well, we already know it can't be this one, right? Because we already talked about that one. That one would shift us 5 units up. Notice, for example, if we put 0 in, well, let's try putting in 5, right? If we put 5 in for x, we'd have the absolute value of 5 is 5, plus 5 would be 10, and that is certainly not 5, 10 for that point right there. We want 5, 0. Okay. So now let's try the next two. If we put in 5 here, we're going to have the absolute value of 5 plus 5, which is the absolute value of 10 again. That's no good. So hopefully this one works. The absolute value of 5 minus 5 would be the absolute value of 0, which is 0. So sure enough, when we put in x was 5, we got a function value of 0, and that matches up right there with what we have, right? So our next step is that when we have some function g of x is equal to the absolute value of x plus c, oops, sorry about that, erase. We're going to be moving, if it's, oops, plus c, we're going to move c units to the left, and if it says minus c, we're going to move c units to the right. Okay. So this one's different, right? You can see that all those values have already been substituted for you. You can see that we clearly can see our V shape. So before we go on to the next slide, stop for a minute if you need to. Think about what do you notice in terms of how the graph, the blue graph, has changed to get to the green one. What we say is that this graph has been stretched vertically, okay, by a factor of 2. It's increasing now at twice the speed that it was before. So it's been stretched by a factor of 2. Had that been a, well, okay, I don't want to give it away. All right, by a factor of 2. Okay, so this constant or coefficient in front of my, whoops, in front of my absolute value has made it so that it grows at a faster pace. This is kind of like the metabolism of your function, right? So it's been stretched by a factor of 2. If we wanted one that instead was going to shrink by half, so rather than being here at 1, 1, it would be here at 1, 1/2. Rather than being 2, 2, it would be 2, 1, and so on, right? Looks something like this. That would be shrunken by half. So now let's see, when we substitute -1, we want to get 1/2. Well, let's substitute -2. We want to get 1, right? So let's see. Oops. So if we try this first one, we have 2. Well, we know that's not right because that's the one we started off with, right? So if I put in that -2, I'd have 2 times the absolute value of -2. That would give me 2 times 2, which is 4. Of course, that's up here. That's for your other graph. So that's not it. Okay. I'm hoping you all already realize whether or not this is the right one, because you should remember that this -1/2 is going to be a different kind of transformation when it's outside. That takes the whole thing and it shifts it down by 1/2, but let's just give it a try. So substitute -2. The absolute value of -2 is 2, and 2 minus 1/2 would be 1.5. So -2, we get 1.5, which is clearly not the thing we want. So that one was no good. Let's look at the last one. 1/2 times the absolute value of -2 would be 1/2 times 2, which is equal to 1. Finally, we got the thing that we're looking for in this graph to match up, right? But the rule of thumb is if you have some function g of x is equal to some coefficient times the absolute value of x, if a is greater than 1, it's going to stretch by a factor of a. If a is between, what am I doing? Had to correct that. If a is less than 1, but of course greater than 0, then it's going to shrink by a factor of whatever that number is. Finally, what happens when we have a negative on the outside of your function? Okay. Once again, we can see how we substituted these values, and if you need to try it, you can. I'm just going to go over the first couple because there is a common mistake. So looking at the opposite, notice that comes from right here, right? That negative was already there in my function g of x. The absolute value of x, and we're going to substitute -2 in place of x. That absolute value has to happen before you can multiply by the -1. Cannot push that negative sign inside the absolute value. So we first take the absolute value of -2, which is 2. And then, bam, that negative hits it, and we end up with -2. So be very, very careful with your signs and absolute value. So once again, I'd like you to take a look at the blue and the red dots, and see if you can determine, here I'm going to go ahead and go to the next slide, what has happened between the blue and the red. Well, you can see that this has gone from being on the top and pointing upward to reflecting about that x-axis and pointing downward. So we'd say the parent function has been reflected about the x-axis, right? So it's gone from facing upward, like a normal absolute value function does, right? Because it should always be ending up positive, to facing downward because you've made it so it's always going to end up negative, right? So if we have some function g of x is equal to the opposite, we have that negative sign right there, that's going to be a reflection about the x-axis. Now, you're also going to be learning about reflections about the y-axis, but the absolute value function is not a real good one to do that with, because you can see if it reflected about the y-axis, it would end up looking exactly the same. So let's look at what we have here. We have a new function h of x. We want it to stretch vertically by 3 and reflect about the x-axis. What would it look like? So stretch vertically by 3, that means instead of 1, 1, it would be a 1, 3. And reflect about the x-axis. So we're going to expect something that looks kind of like this guy down here. Let me make him a little bit more obvious. Let's make him a highlighter. Okay, this is the one we want. I don't know if that helped any. I'm going to say it did. All right. Okay, so you can either just try different ones, but let's see if we can be a little more advanced. Let's see if we can remember where it gets stretched and shrunk. Remember, for stretching and shrinking, that is the coefficient that you'd have right here. Okay. And for a reflection, that's whether it's positive or negative right here. So we know if we want a reflection about the x-axis, it's going to have to be the negative sign right in front. And there we also have, a vertical stretch of 3. Now, just as an extra, so this is our answer. We can check it by putting in some values. As an extra, think for a second, what would this guy do? If you need to pause for a moment and go back and look at the previous slides, you can, or if you took good notes, that would be wonderful. I'm going to give you the answer, so pause if you want. But this would take our function, because it's outside here, and shift it down 3 units. For the next one, pause if you'd like. It would shrink by a factor of 1/3. And this is a little early yet, because the absolute value of the opposite of x is actually equal to the absolute value of x. But eventually, that would be a reflection about your y-axis, where all the positive x's would become negative and the negative x's will become positive. But we haven't quite gotten there yet. So our answer to this question is -3 times the absolute value of x. Okay. So here's one for us to graph and try and make observations. You can see that several transformations have happened here. Okay. If you would like to try beforehand, you can. Okay. And I'm actually going to see if we can't make a guess, right? So making my guess, we've got a transformation here, a transformation here, and a transformation here. That's the one we just did. That is our reflection about the x-axis. This +1 inside with the x is a horizontal shift in the opposite direction, left 1 unit. And this +2 afterwards is going to send us up 2 units. Those are all the things we've talked about so far. The problem is we have to do this in the right order, because if, for example, we went up 2 and then reflected about the axis and then went to the left 1, it's going to give you something different than if you went left 1, then reflected, left 1, then reflected, and then went up 2, right? That's a whole different place. So we have to be very careful in how we do this. Let me erase all that. Ooh. All right, and the order is H, S, R, V. We have to do horizontal movement first, left and right. Then we're going to do our stretching and shrinking. That's the stretching or the shrinking. Then we're going to do our reflections about the X or Y axis. For us right now, it's just going to be about the X axis. And then we're going to do our vertical shifts. Okay. So if we do this in the right order, just keeping track of this point right here, that's the important one. If we go left 1 unit, S, no stretching and shrinking, R, reflect, that going from facing up to facing downward, and then vertical, go up 2 units, we're going to expect that we're going to find a point right here. Let's give it a try. Let's go straight for the -1. So we've got negative, or the opposite of, -1, +1, +2. Be very careful with your signs. Absolute value part first. -1 + 1 is 0. The opposite of 0 is 0. 0 + 2 is 2. I'm liking it. I'm thinking that the way we described our transformations were correct. But let's go back. We're just going to now substitute all these values. Okay, well, you've seen them already. Take a moment to see if you can substitute the values and see what you find. But I'm going to go on to the next one. So pause if you would like to try it. And you can see that we have our V shape appearing here. Okay. Had we not substituted -2, let's just say we did -1, 0, 1, 2, 3, for example, we wouldn't have had that V shape. We'd need to know which way to go. But also notice that by doing that transformation and knowing where that low point was, now we know where our high point is, and we should have something on either side. So I know to go to -2, -3 maybe, and 0 and 1. So I'm going to have some nice symmetry for my values that I substitute for X. It's a little bit above, a little advanced. Right now we're just playing with these things to see how they look. So substituting those values, we should have ended up with those points. Check them, make sure you check your work, and it was correct. Okay. So once again, what happened? H, we went 1 unit to the left. R, we reflected about our, there was no S, H, S, R, we reflected about our x-axis, and then we did our vertical shift of 2 units up. Okay. All right, so what is the shape of an absolute value equation? The key is right there. It is a V shape, and the basic parent function goes through 0, 0, and has a slope of 1 on either, and 1 and -1. Will there always be at least one x-intercept for an absolute value equation? Well, remember, it can move around, right? So we could have something down here that had 2 of them. We could have something up here that had no x-intercept. Will there always be at least one y-intercept? Well, because we have no restrictions on our domain, our x values are going to continue on, and eventually somewhere we're going to cross that y-axis. Does the order in which the shifts are applied affect the final graph? Absolutely. We should first do our horizontal shifts, then stretch and shrink, then your reflections about your x and y axis, and then your vertical shift. You can remember Home Sweet RV or High School RV or something else clever. I've not gotten anything yet. But you do need to remember that correct order of transformations to make it work.